Hi everyone, this is electricity final exam grid questions. So let's start. Identify whether an attraction, repulsion, or no interaction exists when the following objects are brought close to each other. When two glass rods rubbed on silk, they maintain the same charge being positive, so they will repel each other. When two polythene rods rubbed on fur, they, they will have a negative charge, hence repelling each other. A charged plastic rod and a charged glass rod, so positive and negative, they attract each other. So if I show you now the marking scheme here, two glass rods will be positively charged, as you can see, positively charged, repel each other. Two rods will be negatively charged, repel, and a charged plastic rod will be negatively charged. Charged glass rod will be positively charged. Two rods have opposite charges, attract each other. Moving on here, the total charge of the system as shown below is minus 5 units. If 3 electrons are transferred from A to B, what is the total charge of the system? It's going to be always minus 5. Since they're saying the system, not one of the individual blocks, it's going to be always minus 5 due to the law of conservation. It's just the principle of conservation of charge, sorry. So according to the principle of conservation of charge, the algebraic sum of all electric charges in any closed system is a constant. Therefore, the total charge of the system remains equal to minus 5 units. Wait, is my mic working? Hello? Yes. Moving on. Here. For this, you need to know, because it might not come the same, but this is definitely coming, okay? That it goes out of the positive into the negative. The electric field lines, the electric field denoted by E, goes out of the plus into the minus. So this would be out of plus into minus, and out of plus, out of plus. That's it. So go into question 14. Yep, plus minus, plus plus. Moving on here. Consider 3-point charges located at the corners of the triangles. So I've solved this question before. I just have it here. So I'm going to erase it so I can re-explain quickly. Just give me a bit. Alright, just give me a second. Okay, so they want the magnitude of the resultant of Q3. They told you that Q1, so let's just write, they're given Q1 equal Q3 equal how much? 3 microcoulombs. And they told you Q2 is minus 8 microcoulombs. And they told you A is 0.12 meters. Right? So that's A. Okay, so how does Q3 and Q2 act? Q3 will be attracted to Q2 since one is positive and one is negative. Moreover, Q3 would be repelled by Q1 in this direction, as it's true they're both positive. طيب, let's work more with it. They want the magnitude of the resultant force, meaning if you take a look here, let's just draw this. This is A and this is A, okay? And then I have here a right isosceles triangle. So if I continue my propagation here, okay, and then I resolve, my angle here is 45, so my angle here is 45 as well. Why is that? Because in an isosceles triangle, in a right isosceles triangle, one angle is 90 and the other two angles are 45. Okay, so this is 45, so this is also 45. And this is the force F13 and this is the force F23. And this distance is A radical 2. Why? This by the Pythagoras theorem. You should know it. Okay, let's find each individual force. Okay, so obviously this F13, resolve it. It's going to be F13 cosine 45. And then here F13 what? Sine 45. So F13 sine 45. So basically, we need to find the resultant of these three forces. So let me just take just a second. I want to take it on open board. So if I take this, add a new page. Okay. So working with this, let's find first F23 because it's easier. When you have two charges and you're trying to find the force, you do F equal K Q1 K2 over R squared. Okay? So the R between Q3 and Q2 is A, which is 0.12. So K, which is 9 times 10 to the power of 9, times your Q1, which is Q3, which is 3 times 10 to the minus 6. Obviously, these need to be an absolute value. Times 10 to the minus 6. And then directly, instead of it being minus 8, you can just write 8 times 10 to the minus 6, since the absolute value takes the negative away, over the R squared, which is 0.12 squared. Plug in this on a calculator, you would get just a second, you would get 9 times 10 to the power of 9 times 3 times 10 to the power of minus 6 times 8 times 10 to the minus 6 over 0.12 squared. You get 15, right? So you get 15 newtons. So which is F23. Okay? And to find F13, we'll do the same thing. So it's going to be K, which is 9 times 10 to the power of 9, times the charge of Q1 and Q3 is the same. So I'm just going to write 3 times 10 to the minus 6 squared, because they're multiplied by each other. So directly I'm just going to square them over the distance between the two charges is A root 2 by Pythagoras theorem. So 0.12 root L2 square. If you plug it in a calculator, times 10 to the power of 9 times 3 times 10 to the minus 6 squared, over 0.12 root 2 squared. You get 2.8125. But then we need to resolve it into components. You need to remember. So this, I need to find F13 cosine 45. Okay. So I'm just going to take this answer. So I'm just going to do answer multiplied by cosine 45. If you do it on a calculator, you will get 1.477 whatever Newton. That is F13x. Then the F13y, which is the sine component, you just do 2.8125 times sine 45. You get 2.39, sorry, 2.393 whatever. Okay, then we can see here that F3 cosine 45 is in an opposite direction of F23. So what we're gonna do is you need to subtract them from each other. So to find the resultant, so F net, you're gonna do this 2.393 minus 15 squared plus your 1.477. Sorry, my mistake. You should subtract the x components from each other. So you do 1.477 minus 15 all squared plus your 2.393 whole squared. So plugging it on a calculator, you would get 1.477 minus 15 squared plus 2.393 squared. You get 13.73. Let's check if that's right. Yeah, 13.6 here because they rounded it. So I used rounding, you shouldn't, but like if it came written part, there would be many acceptable answers as well in the MCQ. It would be like 13.67 and 8. So that's how to do this one. Bit of a long one. Will it come? I doubt, to be honest, but it could. An alpha particle has a charge, whatever. What's the electric force? So directly you do the formula, your K, Q1, Q2 over your R squared is your electric force. But here they told you there are two, so basically you have to just you take the squared, so it's going to be 9 times 10 to the power of 9 into your Q1, which is 3.2 times 10 to the minus 19 all squared over your R squared, which is 1 times 10 to the minus 3 squared. So let's do that. You would get 9 times 10 to the power of 9 times 3.2 times 10 to the minus 19 squared over 1 times 10 to the minus 3 all squared. You get 9.2 times 10 to the minus 22. Let's check. 9.2 times 10 to the minus 22. Define the electric field at a point. It's where a charge experiences a force. So it's where a charge experiences a force. The electric field at a point is the electric force experienced by test charge Q naught at a point divided by the charge Q naught. So that's the proper definition if it comes. Then they told you another point charge Q creates an electric field around it at a diameter R from Q. Another point charge Q is 5 nanocoulombs is acted upon by an electric force of 2 times 10 to the minus 3 Newton due to the electric field created by Q, whatever was the magnitude of the electric field. So the electric field is your force per unit charge. That's just how it is. So what do we have? We have the force, we have the charge. So direct application is going to be 2.0 times 10 to the minus 3 over your Q naught, which is 5 times 10 to the minus 9, and be careful of your units, please. Plug it in on a calculator. So 2 times 10 power 9 over 5 times 10 to the power of 3. You get how much is that? You get 400,000. Yeah, 400,000. Okay. That's that. What is the magnitude of the electric field at a point? 2 meters. Okay, so another equation for electric field is an E is KQ over 1R. So just direct application. Yeah, KQ. Oh, sorry. So the electric field is actually KQ over R squared. That is my fault. I mix up with another formula. The electric field is KQ over your R squared. So just direct application, plug it in, you get the answer. Moving on, let's see if there's any more good questions. I doubt this is going to come. So 32 won't come. I doubt. An infinite plane sheet of charge has density. What is the expression for that sheet? It's sigma over 2 epsilon naught is your electric field. That's just something you need to memorize. For question 32, if you want to check it out, you can check it out on your own. I doubt it's gonna come. It's not that hard, but I doubt it's gonna come. So obviously this is sigma over 2 epsilon naught. You need to know this because it is coming. It is gonna come. It's a grid. Going on to this question, let's just bring it on to the open board. I don't understand why these questions are grids. مش مشكلة. طيب an electron of mass whatever. So they give you the mass, they give you the V naught, which is the same thing as the V naught x, because as you can see it's horizontal, and the E and the width. Right. So calculate the speed. When they tell you the speed, that means it's the magnitude of the velocity. So you need to find Vy and Vx after it travels, all the time. طيب. Let's go with the V naught y. Actually, first let's find the time taken. So the time taken, what is it? We know obviously speed is your distance over your time. So we know that. What is happening with my mouse? We know that your 2 times 10 to the power of 6 is your 0.25 over your time. So to find the time, just switch them up. So it will be 0.25, I'm just doing it on a calculator, 0.25 over q times 10 to the power of 6. You get 1.25, so you get your time. Your time taken is 1.25 times 10 to the minus 7 seconds. That's your first step, finding the time. Your second step now is to find the individual velocities. So the V naught y. V naught y is your AT plus el V, el Vy, el Vy, V naught y. Obviously the V naught y is 0. And then the A. The A here, the acceleration, is the same thing as saying force over mass into the time, right? But we know also from our equations that your electric field is your force over your Q. So the force is your E times your Q, right? So the Vy is gonna be the Q E over your mass all into time. So the charge of an electron, it's 1.6 times 10 to the minus 19 times your E, which was 3 times 10 to the power of 2, all units. Did that was one? Well, let me check all units. Oh no, okay, alright, so they did this. I bet 3 times 10 to the power of 2 over your mass, which is 9.11 times 10 to the minus 31. All of it into the time we found, which is 1.25 times 10 to the minus 7. Okay, I'm just gonna plug it on my calculator here. So 1.6 times 10 to the minus 19 times 3 times 10 to the power of 2 times 1.25 times 10 to the minus 7 over 9.11 times 10 to the minus 31. Wait, I wrote it wrong. You get 6. How much is that? My calculator is running out. So it's 6.586 times 10 to the power of 6. So, just check. 1, 2, 3. Yeah. Okay. Meters per second. طيب. Let me check لكم مقدس. Okay. Oh, minus. Yeah, I forgot the minus. We got the minus here because it's electron, so it's minus 1.6. Then you need to find the Vx, which is just simple. It's your simple xt, or sorry, the V naught cosine theta, but the angle is 0 beginning, so it just remains the same. So your Vx will remain the same. Then plugging it on the calculator to find the magnitude. So 2 times 10 to the power of 6 squared plus You're minus 6.586 times 10 to the power of 6 all squared. You get 6.89 times 10 to the power of 6. Yep, there we go. So that's how to do that question. This question comes a lot, so please know how to solve it, please. So I believe that's chapter 1. Yes. Okay. Moving on to chapter 2. A circular flat surface of radius 2 cm is placed in a uniform electric field, whatever angle between the normal to the surface. What's the electric flux? So the electric flux is your famous EA cosine theta. So it's just 1 times 10 to the power of 2 times your cross-sectional area. So since it's circular, so it's going to be pi and the radius, which is 0.02 meters squared, times your cosine 60. Cosine 60. So let me just plug it in the calculator. So that 100 times pi times 0.02 squared times cosine 60, you get minus 0.119. So, oh, I got a little bit wrong. Why did I get it wrong? I haven't read that. Wait. Just change that. That's why. That's okay. Try that again. Yep, you get 6.28 times 10 to the minus 2. So I just had my angle in radians. Be careful, your calculator is in the proper unit given for the angle that they give. If he whether he gives a pi over 6, a pi over 3, or in degrees, you just need to be careful. This is not gonna come, although it's a great button. You need to just know this. Just know this formula. Okay. This is definitely coming. For closed surfaces S1, S4, whatever, these charges, they want the electric flux through each of the surfaces. Okay. Yeah. So as I was saying, they want the electric flux. So the electric flux is also your Q enclosed, and that enclosed is a really important part, over your epsilon naught. Okay. So let's find for S1 and S2 and S3 and S4. So S1, it covers this region. So it only has the Q1. So it's just going to be minus 4Q, which is Q1, over your epsilon naught. And that is the S1. Let's check. There we go. Minus 4Q over your epsilon naught. Then let's go with the S2. The S2, as you can see, it covers 1, 2, 3, 4. So it covers all these charges. So why don't we add them up, find their net, and we just directly do the Q enclosed or epsilon naught. Let's do that. So it's a Q1 minus 4Q plus Q, which is Q2. It's minus 3Q. And then Q3 minus 3Q minus 2Q, that's a minus 5Q. And then Q5, so it's a minus 6Q over your normal epsilon naught, as you can see below. Okay. Moving on to the S3 surface now. The S3, it covers 1, 2, 3. So let's add the Q4, Q3, Q5. So the Q3, which is minus 2, minus 3, minus 5, minus 6 again. So minus 6Q over epsilon naught. Then the S4, it covers only the Q5, which is minus Q, which is minus Q over your epsilon naught. What is the magnitude of the thin, flat sheet of charge? It's the same formula we covered a few seconds ago. You don't need to derive it. Just know this. So it's your sigma over your 2 epsilon naught. Okay? Excellent, excellent. A conducting spherical shell having an inner radius of 5 centimeter and an outer radius of 6 centimeters carries a net charge of 9 microcoulombs. If a 4 microcoulomb point charge is placed at the center, determine the charge density. So it has a net charge of 4. Let's draw. Let's draw, shall we? Let's draw. It's, problems like these in physics require a drawing. So there are two shells, and the charge is placed here. Okay. They want to know this one. They want to know here from here. Or sorry, from here. From here. How? What's first? We need to find the charge on the inner surface. On the inner surface. So obviously here, if it's 4 by induction, here is going to be 4, and here is going to be minus 4 by induction. Okay. And then if here is minus 4, here is going to be plus 4, and the total thing outside is 9. So if here is plus 4, then what? Here it's going to be plus 5. Okay. Then let's keep going. So the inner surface, so it's going to be obviously your inner radius. So it's going to be a simple. What do they want? The charge density. The charge density is a Q over A. And since it's a spherical, so it's going to be a minus 4 over your pi r squared. Wait, oh, I did a big mistake. Here it's a minus 4, I just noticed, okay? Because as we said, using the same logic, if here is 4, then here is 4. Okay, then here is minus 4 on the outside, so also here is minus 4, okay, and then here is x. So minus 4 plus that x will give you the total net charge, which is 9, so the x is 13, okay? So your minus 4 over your 4 pi r squared, so plug it in on a calculator. Minus 4 over 4 times your pi times the r squared here would be your 0.05 squared. So you get minus 127 whatever. Minus that. Okay? And don't forget obviously to convert the units. Okay? Then the outer surface, as we said, it's 13. We just fix that. Or ugly 13. So it's a 13. Okay, so instead of that 4 minus 4, you just put 13, and the r squared, because it's the bigger radius, this is the bigger radius, just put the 0.06 squared. That's it. Simple problem. Okay. Moving on. 2 finite conducting sheets of charge are parallel to each other as shown. Whatever, both sheets. What is the electric field at each of the points? So this is simple, your sigma over your epsilon naught. That's it. So you just need to find your sigma and your epsilon naught. Okay? And obviously if they want to calculate the electric field through A here. Where is the okay, so I think they call this plate A since okay, so it's gonna be the E2 and the E1. Whatever, yeah, it's gonna be always the same, just opposite in charges, okay? For question 16, you genuinely just need to know these 2 formulas because it's important. I think it came in the last book. If R is less than R, it's this case, and if it's greater, then it's this case. Obviously don't do the tops, because I doubt that will come. I doubt. A conductor with a cavity charge, whatever, within an insulator, how much is the charge on the inner and the outer surface? So as we logically said, the inner surface is going to be plus 3, right? And the outer surface is going to be plus 6. So you need to be like that fast in the exam. Okay, so as we said, inner surface is going to be plus 3, that's plus 6. If you have any questions, feel free to tell me in the comments. I'm open for questions at all times. Let's see. Now we move on to the electric potential energy. Important chapter. A proton of charge 1.6 times 10 to the minus 19 is placed in a uniform electric field of magnitude whatever directed along the positive x-axis is an important sentence. The proton is displaced by 0.5 meters in the opposite direction of E. There you go. Find the change in potential energy. Okay. Here you need to know if displacement is in opposite charges, sorry, if it is moving in an opposite direction compared to E, then your delta U is positive, and vice versa. Okay, so let's just tackle the problem here. So obviously we know your delta U will be your FD, your simple FD, because it's a work. And the force, it's a QE, so it's going to be a QED. Plugging in the values, so your charge, which is 1.6 times 10 to the minus 19, times your electric field, which is 5 times 10 to the power of 3, multiplied by, sorry, I'm short for distance, multiplied by 0.5. Let's just place down the calculator. 1.6 times 10 to the minus 19 times 5 times 10 to the power of 3 times 0.5. You get 4 times 10 to the minus 16. You get 4. Where is it? There. Okay. Type. A proton of mass this is released from rest. The change of potential energy is this. What is the work done? So you need to also know that the work is your minus delta U. Okay. So in this, so you're just gonna put minus the 3 times 10 to the minus whatever. So it's gonna cancel out, becoming positive, as you can see here. That's what they did. Okay. Question 6. 2-point charges are separated. What is the potential energy? So the potential energy, okay, the potential energy formula, which is your simple KQQ over the R. Okay, that is a potential energy formula. So I don't have any space. I'll just write here. Okay, so your U is KQQ over R. No absolute value here, okay? So if it's negative, it shows the direction of motion. So 9 times 10 to the power of 9, which is your K, times your first Q, which is 7 times 10 to the minus 9, times minus 2 times 10 to the power of minus 9, over your 36 centimeter, which is 0.36. Let's do. So 9 times 10 to the power of 9. Times 7 times 10 to the power of minus 9 times minus 2 times 10 to the power of minus 9 over 0.36. I got a minus 3.5 times 10 to the minus 7. Okay. Just know your formula, guys. Please know your formulas. What is the potential difference? Okay. This is your simple add equations. I call it the add equation. V equal add. Okay. So you just multiply the E by the displacement, so it's just going to be a simple 5 times 0.1, which is 0.5. So 0.50. There we go. Somebody might ask me, why don't I convert first? Because as you can see, centimeter and centimeter will cancel, and they want the potential difference, which is your V. So you get your V directly. That's it. What is the expression rating V and E? As we said, it's the add equation. And it's also this is really important. Okay? Your VA minus your VB. Okay? It's your integration from A to B of EDL. Or they might also write V equals minus minus integral EDL. It came the last period. صح ولا لا؟ It did. Sorry. Okay, so it's important. It's important to note. So what are they trying to tell you? Okay, so you find the expression then. They want from 0.5 to 1.5 at 100 volts. Okay, so the potential difference is 100 volts, and then you do 1.5 minus 0.5, you get 100 meters. Okay, very simple. Moving on, what is the electric potential? Okay, so the voltage as well has a formula. It's a V equal Q, KQ over your R. So just a simple substitution, 9 times 10 to the power of 9 times 2 times 10 to the minus 9, so the exponents cancel, over your R, which is 3. So you can just do on the calculator 9 times your 2 over 3. You get 6 volts. There you go. What is the expression of the electric potential due to a continuous distribution of charge? This you honestly need to memorize. It's your K integral 1 over R dq. Okay, give you a moment to memorize. Moving on. I doubt these two will come as well, you know, just very small. I doubt these two will come, you know, just if you want to do them on, if you have time, okay, but it's also 3.3, so it's not going to come. 3.3 is not included. Got 3.4. Okay. So as we said, they told you your Vy is that, and we know the V is the minus integral of the E. So if I derive the V, I get the E. So it's just a simple 16y minus 2, and they want to know its location at 1, 4, so you just substitute the 4, get the answer. I'll just check. Yep, just substitute the 4, and you get the answer. Obviously don't forget the negative sign, I forgot it. Negative sign, you just substitute the 4, get the answer. Top. Capacitance. A capacitor of capacitance C acquires a charge Q when connected across a potential difference. So it's your famous Q equals CV equation. A 4 microfarad capacitor is connected across whatever. Find the charge stored. So it's your Q equals CV. So you just multiply your C by the V, so it's going to be 4 times 10 to the minus 6. I'm just going to do it on my calculator, times 50. So it's 2 times 10 to the minus 4. Where is it? Or 2 times 10 to the minus 3. Oh, it's 40. Oh, this is wrong, okay. It should be 10 to the minus 4, but minor issue. Yeah, you won't face this in the exam. This is a simple capacitance is your epsilon naught A over D. Okay. So your epsilon naught is 8.85. So 8.85 minus 12 times your area, which is 4 over your distance, which is 3.54 times 10 to the minus 3, because it's in millimeters. You got 1 times 10 to the minus 8 farads. 1 times 10 to the minus 8 farads. 11. What is the maximum energy stored? So obviously the energy equations, which is just capacitors energy equations. Okay. So these are all of them. Okay. But these are all of them. You'll have QV, you'll have CV squared, and your Q squared over 2C. Let's see what we have. We have your your C. What else you have? You have the V. So you have your CV. So I'm guessing it's a half CV squared. So it's probably going to be a half C, a simple half CV squared. Half CV squared. Okay. Capacitors connected in parallel. You just To find their equivalent capacitance, you just add them up. So it's going to be a 2 plus 4 plus 9. That is a 15 microfarad. This is really simple. Okay. Obviously, change it to the units. Then, if it's in series, you just plug on the calculator 1 over 2 plus 1 over 4 plus 1 over 9 all to the power of minus 1. Sorry, all to the power of minus 1. And you get 3.2 times 10 to the minus 6 or 3.2 microfarads. A 4 microfarad and a capacitor, whatever, what do they want? Find the final charges Q1 and Q2. Okay, so again, it's your simple Q equals CV. It's really simple. Oh, where did it go? Where did it go? Did I lose it? Wait, 16 something. Wait. Okay, just a second. Okay, so I was really confused because like I saw here 3.2 and I was like, what? So I realized I skipped the solution, so it was actually 15, okay? But the question 16, I was just really confused. Okay, so they're telling you have two capacitors that were connected in series across whatever. Then the capacitors were disconnected and then connected with the terminals of like signs, which basically means they were connected in parallel. Okay. So now how to solve this? Okay, you just okay. So let's start. So in series, your Q1 would be equal to your Q2 would be equal to your Q equivalent, and then it would be your C equivalent V. Then how to find the C equivalent? It was this one, which we said it was the 3.2. So it's going to be Q equivalent is the 3.2 times 10 to the minus 4 times the 50. Okay, so let's do it. So it's going to be 3.2 times 10 to the minus 4 times the 50. You guys, just 3.2 times 10 to the minus 6, sorry. Minus 6, okay. You get a 1.6 times 10 to the minus 4. Then as you can see, it was connected in parallel because when they say like terminals, so like this in parallel, okay. Then okay, so and then we need to find the Q total. Okay, so we find the 10, it was 1.6 times 10 to the minus 4, yes, coulombs. Then there are two of them, so it's going to be a 2 into to find the Q total. So you're going to get Q total is 3.2 times 10 to the minus 4 coulombs. طيب. Then in parallel your V1 equal your V2 equal your V. This is like a property, you know, from grade 9. طيب. So your Q total now it's a C1V plus your C2V. Why? Because the capacitance now will be additive, okay? So arranging for your Q total, you can take V as a common factor here. So it's going to be V into C1 plus C2. So your Q total would be C1 plus C2. So it's going to be a 3.2. Let me just write it here actually. So it's going to be a 3.2 times 10 to the minus 4, which we found here, over your C1, which is 4 times, it's 4 times 10 to the minus 6 plus your 16 times 10 to the minus 6. That's some calculator. So it's 3.2 times 10 to the minus 4 over your 4 times 10 to the minus 6 plus your 16 times 10 to the minus 6. You get 16. So you get 16. Then with a simple Q equals CV, so Q1 equals C1V. So obviously this is going to be equal to a V. So this is the V in parallel. So your C1 you just do the 4 times 10 to the minus 6, which is the given, times the 16 for the Q1, and then the 16 times 10 to the minus 6 times 16 for the second one. You get the answer. That's it. So let's check. Okay. Yep. Okay. Capacitors are connected in parallel. V. Yep. Okay. Charge on each capacitor. Yep. Yep. Just do the 4 and the 16 times. Okay. This question might come, might be the only difficult question in the exam. It's a little bit difficult. It's not that difficult, but a little bit. Okay. Type. Now moving on to the dielectrics. I think it's just one question, yeah. And I think it's even the last question. Okay. So a student wants to create a simple capacitor using aluminum foil as plates. The student cuts 2 pieces of foil using dimensions, whatever, and separates them by distance. What should be the dielectric constant for a 1 nanofarad? So I think this was a C equal a K epsilon naught A over D. Well, let me check. Yeah, so it's a K epsilon naught A over D, where K is your dielectric constant, so it's a CD over your epsilon naught A. So equal to your K, so it's a direct application. Your CD, your capacitance, which is a 1 times 10 to the minus 9, a distance of separation, which is 2 times 10 to the minus 3, over your epsilon naught, which is 8.8 times 10 to the minus 12, your area, which is this, which is the 0.15 times 0.08, 0.15 times 0.08. Okay, so if you calculate it, let me just put it 1 times 10 to the minus 1 times 10 to the minus 9 times 2 times 10 to the minus 3 over 8.8 times 10 to the minus 12. Sorry for my bad handwriting, guys. Sorry for my bad handwriting. 0.15 times 0.08, you got 18.9, which is 19. 19. So I believe that's it. Thank you guys so much for watching. Good luck. If you have any questions or anything, feel free to comment down below. I would suggest after doing the grids, you go do the past papers, and that's it. Good luck.